So LLVM is great for language conformance and code optimization. This presentation is about why and how we must do the same greatness to build times. We're going to do that through a practical example, then describe the problem space with Alex, and finally roll out the plan. So our case study is going to be game development, C++ game development, AA and AAA. Why? Because it's a great place, it's a great domain to understand the link between creativity and iteration time. So what is the user experience of game development? Well, if you're lucky, and mind you, you're building the game, so you can't just rely on data that you're going to change. That's going to happen once you know exactly what the game is going to be. Then you can build an architecture that is data-driven. But meanwhile, you need to change some code. And if you're lucky, you get some solutions like Live++ that's going to build and patch your change. Then you can play the game and debug and do that again and again. A very short iteration loop of 5 seconds. Most likely, it's going to resemble that, where you're going to have to, from time to time, build your target, launch the editor, compile shaders, and mind you, compiling shaders is kind of a nightmare in game development, especially since the industry has shifted massively to tile-based deferred shading. So it means that you can have not a lot of shaders, but then they're going to create like 2,000 shaders that we call them shader variants. They are code permutations. And that can take a while, even just changing a line of code in a shader. Then you're going to load your level, then you're going to play in editor, then you're going to have to move to the location and go to the context where you can test your change, and then you're ready to debug and go for another loop. That's a long 15 minutes when you're iterating on a small piece of code. But there's even a longer path. There's a longer path when there's interlocks between data and code, and you need to revalidate everything, and that's a nightmare that happens way more often than you might think, and that can take hours where you're going to pre-validate, and you're going to build the whole game, and you're going to build the editor, and you're going to unit test, and you're going to cook maps, simple maps first, so that then your boats can wander around the world and auto-test for regressions in frame rate or memory or things like that. Then you're going to cook all the map, then you're going to package your game, then you're going to sign authentication, etc., etc. It's going to take a while. 2 to 8 hours. Why is that a problem? That's a problem because we are doing gameplay programming, and iteration time is key in gameplay programming. So here's a quick example. I have a camera that follows my character, slides against a wall, but as soon as there's no more wall, then the camera abruptly comes back to its position, and that's pretty ugly. We want to fix that. So at first you're like, okay, I'm gonna just damp my camera. I'm gonna damp my camera. You add a little piece of code here and there, you do some change, then you realize, oh no, wait, I don't want to damp the camera all the time because otherwise it's gonna create a perceived input latency that we don't want. We want to damp the camera only when the sphere trace between the character and the camera collides with the wall. So you do that, and then you realize, no, my assumption is wrong because the sphere trace not colliding with the wall is not enough for me to switch to this damping mode because there might be another wall behind the wall. So, and you still want the nice damping of the camera. So you do it and change, and then you're quite happy, but then you realize that on some platforms, the frame rate is not the same, and the camera does not behave the same because your damping function is not frame rate independent. So you implement some exponential decay, etc., etc., until you reach a very good result where the camera slowly and smoothly gets back to its natural position. And that's the result that you were looking for. And obviously you thought that it was going to take only 10 iterations or maybe 30, and it took that times pi, because that's the rule of thumb in the game industry and probably in other industry, and you end up with 100 iteration. Why is it critical for you to iterate so often? That's not a bug, that's a feature of any creative process. It is critical because, because we are humans, and as humans, we have a mental model of the world that we try to update as frequently as possible for like survival reasons, obviously. So you have a mental model of the world has its own reality. You predict something, you try, your senses perceive the change, and then you update your mental model. That's how it works for everything, every interaction. And when it works really fast, then you can use what we call proprioceptions, where the tools you're using become an extension of your own body. And then you can enter this flow state where things move as if they were part of your own body. And that's the fundamental difference between craftsmanship and engineering. When you can enter this back and forth loop in less than half a second, then you can start to really be creative, even expressive, and improve the game feel. And if you do that enough, you become even an artist of any topic that you're tackling. For us, it's about solving problems. It's about staying focused on trying to bring the better here, for the example of gameplay programming, the best game feel for the player. But it means staying focused, and that cannot happen if compiling takes forever. And it's not just the only hurdle that you're gonna encounter, because there's a whole lot of ripple effects. For instance, obviously, iteration time will influence time, and time is money. And money and time, losing money and time, creates frustrations, and frustrations create a lot of lack of motivation, obviously, and etc. And all that echoes itself. But I would say that's not even the worst. The worst is for the end user, here, our player, because they won't get the quality. There's no way in a world where you're gonna iterate, one iteration loop will take hours. There's no world where you're gonna iterate 100 times on a camera. What will likely happen is that you're gonna drop the ball and just call it good enough as soon as a problem is fixed, but the game feel won't be there. So that's the biggest cost. I'm gonna give the mic to Alex, yes, so he can dig a little bit more on the issues.
So we're gonna see some specific issues that can be addressed by LLVM. So I'm gonna ask you some questions if you want to answer. Why do you think this performance is different for these two users? So essentially we have a game that's been built by two different users, same hardware, same game, same code. One of them has good compilation times, the other one not so good. So what happens? What do you think happens here? Mini filter drivers. So Windows has this great concept that essentially has drivers that insert between the user space and the actual driver, device driver. So these mini filter drivers live in kernel space, and they can do anything they want. So that could be compression, could be encryption, security stack, anything like this. So in this case, the user had some driver that has had contention. Another example, same kind of stuff. Here I'm compiling Clang with TinyLTO. So what do you think is different? What has changed before and after? So here is the CRT allocator. Another problem that it's very common on Windows. Essentially, the C allocator, the heap allocator is logful. So as soon as you have many cores in the machine, well, you have this kind of issue again. So again, these kind of issues are really hard to spot because you see some effect there, but until you actually capture a trace, you don't know really what happens. Another example of this, here I've spawned a VM in the cloud. So I'm compiling LLVM, just running check all. You can see that on Linux takes like 1 minute, on Windows takes like over almost 10 minutes. So it's another example of other things that can happen on Windows. In this case is the starting and shutting down of the processes, which is really slow on Windows because of many reasons. We can go into details, but essentially it's contention. We see a lot of contention on Windows. So I've been saying that for years. I think Windows is great. It's a great OS. Yeah, there is a lot of, it's cohesive. It has a good history of backward compatibility, but it has these issues that the user should fix if you want a good performance. So the end goal, the end problem of this is that it gives an inconsistent experience across machines. Something different here. We have an Unreal Engine game. We build it. So when we build that game in non-Unity build, which essentially is compiling each translation unit on its own, all this generates about 270 gigabytes of data. Then when you link it, it goes down to 2 gigabytes. So that's a lot of churn there, a lot of data that was generated. If we build the same game in Unity mode, meaning that we aggregate the translations units together, the size is smaller. The build time is also smaller. But it's the same issue in the end. It's the fact that we have so much data, which ends up being discarded in the end. So again, this is a problem. It's time, energy that it's spent somewhere. Another thing, why is it that the source file always looks new every time that you invoke the compiler? So I think this is how it always worked. Like goes back to past maybe 50 years ago. But the reality today is that the code is actually a causal graph in a project. So it's just small changes that you make across the lifetime of that code. But the compiler only considers the current snapshot, actually the inputs that you give it. It doesn't even know what the project is. So it would be really nice if it knew all this permutation, this hyperspace of changes. Another thing that it's also hurt, I think, it goes with what I said before, is the fact that the toolchain cannot live on its own. It needs other tooling, like the build system, like CMake, Ninja. It also needs some kind of build acceleration because the code is really, really big today, and you cannot possibly compile everything on your machine. You can, but it's slow. And also, there are some cases where small studios cannot afford like big machines to compile this kind of engines. There have been some experiments with internalizing these things. Like I think one of the most promising one is the LLVM CAS, which I think is really, really a good avenue forward. So next, I'd like to go through some suggestions, a plan that I think we should do. I'm taking a few assumptions here. It would be really nice if this plan worked for just the golden path. We don't have to support all the cases that LLVM supports. So if we can prove that it works for this golden path, we'll see for the rest after. So essentially, I'm saying Windows, large projects like Unreal Engine or Chromium, deterministic, everything, nothing changes between the build, during the build, modern languages, etc. So I think the first thing we should do is in-process compilation. I'll go in more detail after. The second one is the multi-threaded in-process compilation. Also, the build daemon that has been discussed in the past. I think there's a post from Reed from about like 2013 about that. So it's an old idea again. And I think all these three things could unlock other topics, other things that we can do after to really improve the build times. So the first step, the in-process building, the goal here is to be able to compile these files in a single process, not multi-threaded, but inside the single process. So that means running the tools one after each other in the LLVM driver. In this case, we're using the tool context for storing the state. And we ensure that there's no leaks between running each tool. So there's a few things to change for Clang. For example, it enables the disable free flag for every compilation right now. Also, the integrated CC1 doesn't work if you have more than one job. And if we disable free, we need something like LLD in test, which essentially runs the same test twice in the same process, just to validate that we're freeing everything. So all this is already supported in LLD. LLD already can run several links, one after each other in the same process. So we have to do the same thing for Clang. The second part of this is the multi-threading, I think, would be good for performance reasons. So the big problem there is the global state. There is nothing new there, but I think many of you are aware of that. So we have to choose also which managed static should be too local or process-wide, etc. And at that point, perhaps like a tool thread pool for the single process. This is already in a branch there at the bottom, and the same applies for the previous slide. I'm sorry, I forgot to say it, but at the bottom there is a link with the actual testings, which already cover all this. And the third step would be the build daemon, which can be done in parallel with the other steps, which essentially is a long-running service, like a bit like ClangD. And there we can launch either another process, which is the in-process executor, essentially, or a pool of processes. And we have to find a way to actually communicate with existing build systems. So that could be a communication protocol like LSP, extending LSP, for example, or something different. So once we have all this, I think we can do some other nifty things like caching, all sorts of caching, incremental compilation, on-demand debug information. Again, we generate a lot of debug information. Most of those 200 gigabytes before is debug information. Incremental optimization as well would be really, really cool. We already have a case right now with Live++ that works. Essentially, if you're running a release build and you have Live++ connected to the process, it can de-optimize the file and patch the runtime, and then you can debug it. So it's really nice, but it's external to LLVM. It's a bit brute force. So let's join forces. I think the LLVM community always has been at the forefront of innovation. So I think we should take a lead on build times and not wait for these things to change elsewhere. Thank you. Any questions, please? Yes.
Hi, so out of curiosity, I actually wonder, would you happen to know what happened to this program repository project? Because I remember this a few years back, there were a bunch of LLVM conference talks, and then the project was kind of canceled at some point, if I recall correctly. Would you happen to know what was the reason for that?
Yeah, I think the LLVM cast will just be better than what was done in the end. So I think the first step is to just land the LLVM cast, and then we'll revisit the program repo.
Right, makes sense. Thanks.
Yeah, it didn't give that much improvement in the end. That's, I would say, the main goal, and some of the things had to be redone. Yeah.
Any other questions?
I remember at some point there were proposed compiler changes to try to make Unity builds work better. Did that ever go anywhere? Is that, I vaguely remember some discussion about like modules versus Unity builds. I was kind of curious what the current status of all of that was.
I don't think a Unity file are as good as, I mean, I would like to get rid of them in the end and just use the regular build pipeline and have these kind of things being done in the compiler, like the caching, like I was suggesting, and preamble like headers and stuff like that. I mean, it shouldn't be the user that should be doing that, I think. Yeah. And it's the same thing in Rust. The Rust does the same kind of thing with the codegen units because of the same problems. Yeah. So essentially everything that I said here is the same. When you compile a big code, a Rust code base, you have the same issues.
Thanks.
Okay, well, let's thank the speaker.
Thank you.